So this is our toilet units that are made from used billboard fabric, which is a plentiful resource in the United States. It has excellent engineering properties because it has to be a billboard, and then we found that we can use it for building structures, in this case toilets. We found a way to basically make a really, really inexpensive yet strong and robust, lightweight structure for the toilet. So the walls, it's a lattice with the fabric around it, and then when it gets bent into shape, it tightens up, and so you get a wall structure that's quite solid. Similar with the roof, we're able to shed the water. The units don't weigh very much, so they're very easy to transport. The interface here could be any type of a UD squatting plate. It could be a pedestal, or it could be any type of interface. But we have cleanable surfaces. This vinyl billboard is very cleanable, so it helps for hygiene. We're not dealing with wood surfaces. We want to have a self-closing door, and there will be a latch eventually, so that it can be locked from the inside.
It's kind of a honeycomb setup.
Yeah.
So you can put in quite a few over the surface area.
Exactly. So by having the honeycomb setup, we end up with some synergy as far as the structure goes overall, which is important with a lightweight structure to have the ability to resist overturning from the wind and so on. So we've tied it to the sandbag foundation, which you can see clearly here. Because the units are so light, we hook it to the sandbag foundation. And this is just material from the site that you would rake as you're preparing the site, and you'd fill up the bags and then put them into place and put the unit up. This also helps to, if you have high water table, you're going to keep the water out of the area where you're collecting excreta. And we also use the sandbags for the steps. That makes it for the amount of material and cost that you're carrying into the field, it's actually quite low, because you're going to then do a little bit of labor to put it together. The key thing about the reason we call it Aerosan is because I'm very intrigued by the idea of using air not only as odor control, but also as a way to move a lot of air through the system to promote aeration, aerobic composting, and a degree of desiccation. If you notice, we have a very large ventilation plenum. This is nearly 1 meter in diameter, and the idea is we're getting a venturi over the top, which is creating a wind-driven flow, and then also any solar gain on that plenum is, of course, heating the temperature up inside, and you're getting a solar-driven movement of air as well. So those two things together promote continual passive ventilation. Of course, the wind might be 24/7. The sun, of course, is only in the day. But by doing that, we're finding that we're getting a lot of air through the system, which controls the odors. The intakes in the toilets mean that the odors are going down. All of the material is collected in a tray, which we'll see in a second, so no excreta ever touches the ground, and then the tray can be taken out and to get the material.
The urine is not diverted?
Well, it could be. In this case, in Haiti, where we first did this, we thought we'd do things a little simpler there because we were already having a fair enough challenge. So we said, let's put everything in together, and let's throw in sugarcane bagasse, and let's basically build a compost pile in situ under the toilets, knowing that we would then pull it out and treat it more later. What we found after going back to do maintenance is that there was quite a bit of volume reduction that was occurring, and we were thinking it must be because of this continual airflow. And so, which meant there's less maintenance, the maintenance schedule was longer, and which benefited, the maintenance workers because they didn't have to work as much, and then, we could still took the material out to compost it thermophilically to get to temperatures of between 65 and 70 degrees, which we achieved very easily. And we turned it and achieved them again. We did that 5 times. So that's what made us think that the aeration is actually really, if you have continual airflow, you're really going to have a good effect on that volume, not filling up. The tray right now is not moving because my sandbags have moved a little bit, and so it's not going in. But this would roll in so that those points would be in there, and this would be completely sealed. This is an intake along with the 4 toilets, and the surface area equals that of the top of the unit, which is what promotes the most ventilation. The whole way that this structure is made so easily is we make these wood rings, and this is just scrap wood that we bend. It's very easy. We don't have to get it wet or steam it. We bend it in a form. And this is one of the early rings, so it's a little rough, but this is what these rings are what give all the strength to this entire structure. And loads are transferred because the rings are tangent to each other. So when you stand on this toilet here, load is getting transferred clear out onto the perimeter. So it makes for a very stable unit, which is something that I personally, in Haiti, I walked into a lot of toilets where I thought I might literally fall into the hole or fall into the sides or hurt myself. So I wanted to have a stable toilet. That was just a structural thing that we wanted to have. So, but the building style, to have a plenum this large, you wouldn't do this out of traditional materials like PVC. It would cost a fortune. So the building style allows me to play with some engineering ideas that I've wanted to do, which is how much passive ventilation can we get with a really big tube? Because this tube, I'm guessing the materials in this tube are maybe $30 or $40 at the most. The entire 4-toilet array with the tube and the tray, including the toilet inserts, which are not currently in there, the cost of materials, just the cost of materials, is $525 US. Now, the labor to put it together is additional, but this represents an extremely low cost, but what I think to be a very stable and strong and weather-resistant toilet. And even if the process, so from this point down, if somebody were to say, we're going to do a different process, we have our magic treatment option that we're going to use, that would be fine. We could provide the structures, and it would be the interface, and then they could do process. We happen to like the aeration and composting as our process of choice because it is very effective. And studies have shown from writings clear back as far as the 1930s, where they've studied specifically Ascaris lumbricoides. Gerald Winfield and James Cameron Scott in China did work there and studied the effects of thermophilic composting on Ascaris viability reduction. And the numbers, after 36 days and 5 turns of the compost, they show the temperature spiking and then going back down after each turn, and the viability of the eggs going from some number, I don't remember the high number, but it went absolutely to 0 in 36 days. This is not known, I think, in the Ecosan world, and I think we need to revisit those ideas a lot. So.